Hello everyone, my name is Ian Stone, and I'm going to take you guys through the last decade of hypoxia in Muskegon Lake and what is driving it. So first off, what is hypomagnetic hypoxia? For our purposes, it is concentrations of dissolved oxygen in the bottom layer of a stratified water body between 4 and 2 milligrams for mild hypoxia and beneath 2 milligrams per liter for severe hypoxia. So this is caused by any number of things, including water column stratification, meteorological conditions, and biological respiration. And that biological respiration aspect is very important to look at because it has lethal and sublethal effects on the fish and macroinvertebrates that require oxygen for that respiration. And so using data collected from the Muskegon Lake Observatory buoy, we've seen over the last 10 years a slight decline in the number of total hypoxic days where hypoxia reached that 4 milligrams per liter threshold. And so I wanted to look at it a bit of a different way, to look at the average concentration that's per day for each year. And so there's no real discernible trend here, though 2019 did break a bit of a 5-year decline in dissolved oxygen. And so then I wanted to look at the two most and least severe years, which ended up being 2011 and 2012 for the most severe, and 2015 and 2019 for the least severe years. And that was calculated by the equation you see at the top of this slide here. So that data was tested using a couple of statistical techniques for a number of variables, including chlorophyll A, air temperature, top and bottom water pH, and top and bottom water temperature. So beginning with chlorophyll A, we can see that the severely hypoxic years showed a considerably higher concentration of chlorophyll A, and that's no surprise as those years had large algal blooms contributing to that high concentration. And this also followed a general decreasing trend of chlorophyll A in all of Muskegon Lake throughout the time frame. As for air temperature, if you look at the years as a whole, there's really not a lot of variation between them. However, when you break it down into the seasons, spring, summer, and fall, we can see that 2011 and 2012, our severe years, had considerably higher average air temperatures than 2015 and 2019, our least severe years, although 2015 and 2019 did show higher fall temperatures. And so this could be contributing to stronger and longer stratification in those severe years, which can also lead to the decline of oxygen in the bottom waters. As for pH, we start by thinking about the equation for photosynthesis and respiration. And so it makes sense that bottom water pH at 11 would be lower as you have a lot more respiration, contributing more CO2 to the water column there. 2011 was a bit of an anomalous year due to its very high pH in bottom water. And so you would think that 2-meter pH would be significantly lower in the mildly hypoxic years due to less photosynthesizing algae to absorb CO2. And 2011 was an outlier year, like I mentioned, but when that year is removed, there was really no significant difference between the years, though you would expect a lower pH in years with large algal blooms and severe hypoxia contributing to that respiration. But we didn't really see that. In fact, we actually saw a bit of a decline in pH. Or a bit of a rise in pH, sorry. And then when putting that into a PCA form to look at the individual variables and how they affect on a temporal scale, we can see that there's a slight shift from the lower right to the upper left corner, and that's driven mainly by a decrease in chlorophyll A, 2-meter pH, and 11-meter pH, and increases in 11-meter and water temp and 11-meter DO. So then, to wrap up here, hypoxia is still prevalent in Muskegon Lake, and it probably always has been, though we're looking to get that number down. It has shown a decreasing trend in the last 10 years, which is very good for getting Muskegon Lake delisted as an area of concern. And the lower spring and summer air temperatures likely led to a decrease in stratification for mildly hypoxic years, giving it more potential for mixing and higher hypomagnetic temperatures. And then the variation between the years was most strongly explained by decreasing hypomagnetic pH and increasing hypomagnetic water temperatures. And that's all I have for you. Thank you for watching this.